Yes, so welcome back. Um, I think I'm the person standing between you and the dinner, right? So I'll try to keep it somewhat brief. If there are certain concepts that are not clear, there definitely will be some concepts. We can discuss them in person if you want to do that, okay? So I'll just get going. So today, so propagation path here will be that we'll start off with some things that we left, right? So we're going to discuss the TD-DFT fundamental equations, right, and go all the way to dynamic polarizability. So, and this was in some way, some part discussed also by Arun. So, it will be a little bit of a refresher for you. And then I'll connect the polarizability or the response matrix to the interacting response function in spatial domain, and then how one can use the spatial response function to compute ground state correlation energy. So that would be the connection between, say, TD-DFT to RPA, the random phase approximation that I'm going to discuss, and then I'll discuss a couple of applications for that. So it's a lot of things, so we can stop wherever we want, and if required, do a separate discussion, right? So I think the first topic of discussion is our perturbed density matrix. We discussed that in last meeting. We said we are going to apply a perturbation which is in this particular form, G of PQ, right? And this has been written deliberately as a Hermitian form. And once you apply this perturbation, this is a non-local perturbation, I'm going to have a perturbation to the density matrix which has been expanded in the following form, right? And then I discussed that there is a simple Fourier transform, the Fourier component of that particular density matrix. We could write it in this form. So what remains to be done is to figure out these unknown coefficients D. So these are the Fourier components corresponding to this particular frequency. And I also said the constraint here is that we're going to have to impose idempotency at all orders, right? First order, second order, and so on. We are interested only in the first order density matrix at the moment. So once I impose that constraint, right, and we know how the ground state density matrix looks like, once I impose that constraint, I get the following. I get all components belonging to occupied or virtual. So I denotes ij, indices denote occupied orbitals, A denotes virtual indices. Those are going to contribute 0. So the only variations that you can have to the density matrix would be coming from occupied virtual or virtual occupied. So this is the only component that we need to worry about. So that you have to figure out, right? So that is yet to be done. So how do we do that? For that, we're going to use the von Neumann equations of motion, right? So we have this simple von Neumann equations of motion, and how to solve it, I still don't know how to do that, right? But what we will be doing is simply doing a first order perturbative expansion, right? So once you do that, so you look at this equation, you have to expand this order by order, and we are going to only collect the terms which are first order in the perturbation. So I'm going to have F0 P1 and F1 P0 giving you I dP1 by dt. So these are the first order corrections, right? And I just want to mention what is a form of perturbed Fock matrix, right? So the perturbed Fock matrix will have your external perturbation G, and then there is a chain rule, right? So there is a chain because Fock matrix itself depends on the density matrix. So f of t depends on density matrix. So you have to consider this particular correction, right? So once I do that, so if I now expand my perturbed Fock matrix, so what do you see there? So there is the perturbation, the external perturbation, and then once I apply this perturbation, I have to take a derivative of the Fock matrix with respect to the density matrix. So once I do that, I get this 2 electron integral. So I have the Coulomb integral PQSR, right? And I also have an integral over the exchange correlation kernel, right? So FXC. So that is the main, these are the two main terms that we have here. I'm going to write them in a combined format and use this particular symbol, okay? So if my Fock matrix was truly independent of the density matrix, you would not have these other terms because it is dependent on density matrix. You have these additional terms, okay? Now, other thing I'm going to use here is the so-called adiabatic approximation. So what that means is this Fock matrix is going to be evaluated at a given time, so not this Fock matrix, FXC. This FXC matrix will be evaluated for a particular density at that particular time, right? So that will make it instantaneous in time, and as a result, I'm going to be using the frequency independent or time independent curler here, right? So the adiabatic approximation is going to be used here. If I don't use adiabatic approximation, this particular term will become frequency dependent. This is what Arun had shown, right? So when Arun was writing out the equations, he had the time dependence or the frequency dependence in this kernel. Because of the rho inside.
Rho is periodic.
Periodic, right? So frequency dependence does come in there. Yes, I'm going to neglect that, right?
That's what your RPA.
Yeah, that RPA is not that. RPA will be where, yeah, RPA will be where I'm neglecting the whole thing. That is slightly
not
different.
Just FXC, the whole thing.
Whole FXC. I'm going to neglect this whole thing. That will be RPA.
FXC, yes.
Exchange correlation, that is RPA. Yeah. Okay, any questions so far? So right now I have made an adiabatic approximation, which means this particular rho is no longer frequency dependent. So that is the point over there. Any questions? Yeah. Right. So now I can go ahead and figure out those unknown D's now. As I told you that the D part is the unknown, right? And I need that occupied virtual kind of combination of these D's. Yeah.
If I'm allowed, I'd like to make that statement more
Yeah.
expanded way and elaborate on this. What the adiabatic approximation would mean. See, generally, when you write a response function, so disturbance at R prime can create some change at R. Similarly, time dependent, disturbance at T prime can create later. Adiabatic approximation, I'm saying it's local.
Yes.
Whatever I'm doing now, it happens now.
Right.
No other changes.
Right.
It's in that sense that you're making it.
Right. So the adiabatic approximation means that your disturbance is local in time. So you have a delta t minus t prime.
So any change at time t equals say 5 seconds, the effect at 5 seconds.
Yes. So it is t minus t prime. So you have the delta function there, but it is still non-local in space, right? So that we have to remember here. So the non-locality in space is present. It's present in both the so-called Hartree kernel as well as the FXC kernel here, right? But Hartree by definition is local in time. Okay, so that there is no time issue there. But the exchange correlation kernel, there is a dependence on time, and that is being neglected here. Okay, so and as I was saying, we are going to use this couple of the outcomes we had from the previous slide was that these terms are 0, and I'm going to call DAI as XAI and DIA, right? The transpose of that as YAI, right? So we are going to use these things, and also remember the density matrix in the ground state. Sorry, this should be ground state is going to be diagonal, right? So and now once I do all that, I'm going to collect all the terms which are going to go with e power I omega t or minus I omega t. I'm going to get two equations over there, right? So after doing all the simplification, I'm getting these somewhat complicated looking equations. So one equation is for XAI, the other equation is for YAI, right? So these are the two perturbations that I'm going to have here, which I have to figure out. So my unknowns are X's here, right? So that's the first order perturbation I have to figure out in the density matrix. But what you see here though is that these are coupled set of linear equations. Everything is linear, right? The X's and Y's are appearing linearly in these equations. Is that clear? And they're coupled set of equations, right? So I have to solve for this coupled set of linear equations. So that is the unknown part over there, right? So, and I'm going to evaluate the whole thing in the limit Fia is equal to 0. That is the perturbation that I'm going to be applying. So that is going to be vanishing, okay? So once I do that, but my frequency is not vanishing, okay? So that keep that in mind. So once I do that, I get this very simple equation over there. So one for XAI and another for YAI, and you see a bunch of terms appearing over there, right? So if I rearrange all of that, I'm going to get a very simple matrix equation, which is what Arun had shown before, and probably in other talks as well, where I have the following form of the matrix AB minus B star minus A star XY equal to omega times the identity matrix times XY. Okay. And what are the elements? So the element of A for AIBJ is the Kohn-Sham orbital energy differences and the 2-electron integral evaluated over the Hartree exchange correlation kernel, right? So that is what we have. Similarly, you have the elements for the B matrix, okay? Now let us just concentrate on this particular form. I'll slightly write it in a different way here. So you can see I have written the same thing, but I multiplied this from the left side with 1, 0, 0, minus 1, and then I get this particular form of the equation, right? So can you tell me what type of equation this is? So is it an eigenvalue equation, something else? So any thoughts? Is it looking like an eigenvalue equation? Looking like, but what is the main issue? This particular thing, right? So what you see there, this is called a symplectic eigenvalue equation. So it is not your regular eigenvalue equation, and it is because of this particular matrix appearing here, okay? You find such equations in a lot of, I think, control theory type problems where you have to figure out stability and so on, right? So you get this symplectic eigenvalue equation. So you can't use your regular eigenvalue solvers for this particular equation, right? So you can't really solve it. So how do we solve that? So that is one question, okay? And the other thing I want to point out is that this A matrix can be related to as a matrix element of two singly excited Kohn-Sham determinants, okay? So the A matrix can be related to that. And the B matrix can be actually related to the a matrix element between the ground state Kohn-Sham determinant and a doubly excited Kohn-Sham determinant. So you can say that A matrix includes effects of single excitations and B matrix includes effects of double excitations, okay? So you can think of it like that, okay? Right? So how do we solve it, right? So this becomes a little bit of a tedious problem. One simple way is that you completely neglect the B matrix. That is what Arun was talking about. So if you neglect the B matrix, this is called the Tamm-Dankoff approximation. You get a very simple eigenvalue equation, right? So this is the thing that you had here. So if I just simply neglect B, I'm going to get a eigenvalue type equation, okay? So that is one way, and this is exactly equal to what we call as configuration interaction singles, right? So this is one way to get things out. It turns out to be a nice approximation, actually, the Tamm-Dankoff approximation, okay? Now the other way is to turn this into a eigenvalue problem. How do we do that? We simply actually expand these equations as two linear equations and then add and subtract them, right? So once you do that, you can turn this equation into the following. You have A plus B times A minus B, and then you have to solve for, say, X minus Y. That is, now it looks like an eigenvalue equation. So you can slightly modify this, multiply this with A minus B half, and you can separate this into two A minus B halves. And then you can turn this into an effective eigenvalue equation where you're solving for, say, something called mz equal to omega square z, right? So now you can apply, say, something like a Davidson algorithm and to figure out a few lowest eigenvalue equations, okay? So what is m there? M is A minus B half multiplying both sides the A plus B equation, A plus B matrix. And your eigen functions are going to be A minus B half times X minus Y, okay? So you have turned turned a non-eigenvalue equation into an eigenvalue equation, but the eigenvalues you're going to be getting are omega squares now. So you'll have to take the square root of that to get the correct eigenvalues, okay? The other thing that I would like to mention here is that this particular matrix, A plus B as well as A minus B's, these are called orbital rotation matrices and second order orbital rotation matrices. So they are related to the stability of your wave function with respect to orbital rotations, okay? So many times you would have run a Gaussian program or, say, NWChem or turbomole, and then you would try to do, say, TDDFT, and suddenly there is a statement which is saying that you have a singlet instability or, say, a triplet instability, right? So why do those appear? Those appear because, say, this particular matrix A plus B is not positive definite, Okay, so there is a solution which is going to be lower than, say, your ground state solution, whichever you started off with. So if you have that, you're going to have negative eigenvalues of A plus B. Okay, so if you have that, you are going to have a instability. So you can have instability in A minus B, you could have instability in A plus B. So A plus B's instabilities could be due to singlet instability or, say, a triplet instabilities. These are common instabilities that you have. Okay. For A minus B, in general, when you're dealing with real orbitals, it is going to be positive definite. But you could have complex perturbations. Okay, so non-real perturbations. So if you have non-real perturbations, your A minus B will also have negative eigenvalues. Okay, so you need all of these matrices to be positive definite to get the right positive omegas. Okay, so that is the main thing here. Okay, so I hope you can relate your now the TDDFT matrices to instabilities. So I think I hope that is kind of clear. Okay, yeah. Any questions here? And what is, yeah?
So if we are working, these are generally seen as de-excitation. You mentioned them as double excitation. I could see there's not 5IJ.
Uh,
B is generally considered as de-excitation.
so yeah, so I don't know how to answer that. So how B is considered de-excitation?
These are generally
The B is the coupling between the cone sham and the doubly excited determinant. Right. So no, so you can I'm saying yeah. So you can interpret that matrix element as the coupling between the ground state and the doubly excited determinant, right? So there is no explicit A dagger, B dagger, IJ. There is no explicit term like that. But you can interpret the B matrix as the doubly excited determinant, right?
usually if you see in papers and all, they normally call it de-excitation. Right? So I am trying to understand what is the, how are you connecting it to double excitation at the same time?
So if I think about these integrals that we have, right? So the integral that we have here, AI Bj, right? If I were to start from the ground state, the only way I would get that is via double excitation, right? Right. I mean, see, if I really think of an excitation picture, right? The singles, they're obvious in the A matrix. So what is really B? So now you are trying to say it is a de-excitation. Okay. For me, it is looking more like a double excitation, I guess, right?
Occupied to unoccupied and unoccupied to
So the reverse.
yeah, this is just the coupling matrix. This is how it's being written.
Okay. Okay. So you
So the XY is that go from because if you see the roots, we do get let's say occupied to unoccupied and then unoccupied to occupied configuration.
right.
We never get a double excitation configuration. It's not a double excitation. It's just a cross coupling.
I think yeah. Right, right. So you would see this in literature, of course, but I think you can turn the couple cluster equation into this form, the couple cluster doubles equation into this form. I don't know if you are aware of that literature, right? So the doubles are there in this particular form, right? So I guess it's how we want to interpret it. I think that is where the question is. So I would write the couple cluster equation A plus BT and so on, right? If I were to write that, and if you turn that into this particular form, you will see there are doubles there, right? So how?
It's the same coupling that we get there, and
Yes, yes, yes. So you can write that. You can write the Riccati equation, and you can turn this back here. Yeah. Okay. So any other questions here? Okay. So the other approximation which is commonly made here is called the random phase approximation, and the name random phase approximation has its origin in condensed phase physics. So I don't want to go too much into that. But in random phase approximation, you're going to neglect the exchange correlation kernel completely, fxc equal to 0. So that is random phase approximation. You normally don't do that in TD-DFT calculations, okay? But we're going to discuss something called ground state correlation. So over there, this particular terminology will become useful. So fxc being 0 will give you what is called as a random phase approximation, okay? So just keep that in mind. So once you do that, you only have the terms coming from the Hartree kernel. Okay, so you have completely neglected the exchange correlation. Okay, so this is some terminology for you, right? And now let us come back to dynamic polarizability. So now that we have set up the fundamental equations for linear response TD-DFT, right? So now if I have a perturbation which is a dipole perturbation, and let us say I'm applying in x direction, and I want to measure the response in the dipole response in the y direction. So that is alpha yx, okay? And it's a frequency dependent response that I want to measure it, right? So if I want to do that, I no longer neglect my perturbation. I have my perturbation on the right side, and I have to figure out the response, okay? And what would be the response? Response would be just the inverse of this whole thing times the perturbation, which is my mu vector in the x direction. So once I have that, I can now go ahead and compute my alpha yx of omega, which will be just the trace of the mu vector and the response vector. Okay, so you have applied a perturbation, you got a response. That response times the direction in which I want to measure the response, mu y, that will give me alpha yx. Okay, so the term in its full glory will be the mu vector times the inverse of this whole response matrix times the mu vector again. Okay, so this is going to give me the dipole polarizability. Okay, frequency dependent. And if I want the static polarizability, what do? I just make my omega 0, right? So that will give me my static polarizability. Is this okay? So you can connect your dynamic and static, obviously. Okay, so this is how we can go ahead and we can get our dynamic polarizability in linear response TD-DFT. Okay. So any questions so far? Right. Huh. Right. So for beta or say the first hyperpolarizability, you will have to now solve the second order equations, I think. Yeah. Right. This is linear response. This is dipole polarizability. Yeah. So it turns out the nonlinear coefficients can be, the nonlinear response can be, for the first order nonlinear response, can be written purely in terms of the xy vectors, the first linear response. So there is a relationship between the linear response and the first hyperpolarizability that you get. So that can be done. Beyond that, you will have to solve new equations, right? So I think ground state you have this 2n+1 type of rule. So similar rule also is present here. So you don't have to solve second type of equation. There's a relation between this and right. Okay. Any questions? Okay. In the like in a numerical fashion or okay. 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 So you actually apply a perturbation and then you not analytically like this. Yeah. Okay. Yeah. So this is how most codes do it, right? So you can give a frequency and then you get this alpha yx of omega out, right? Okay. Right. So now I'm going to take you to the world of spatially dependent linear response functions. So what I had shown you was there was no spatial dependence so far, right? So we could also get the spatially dependent linear response function from these matrices, right? Yeah, so how do we do that, right? So what is the connection between the spatial connection to the spatial response function? So I'll just introduce this very simple notation here. So if I want to get the spatial part of the response, I have to project the xy vectors to a particular point in space. Over here, I'm still considering a non-local spatial dependence. So once I project it, I have to expand my x and y vectors in the basis of phi I, phi is. Okay, so I just expand this. And if I were to do that expansion, so now you're going to do it over all the occupied virtual pairs. So you have xai times phi r prime, and so on and so forth. Okay. So now from there, I can get the particular form of a density matrix response function here. So pi r, r1 prime, r2, r2 prime. Okay. What is a density matrix response function? Okay. In space. See, when we were discussing alpha, you had applied a dipole field, and then you figured out what was the induced dipole in, say, another direction. Over here, I'm going to apply, say, some sort of a point perturbation, which is non-local, r2, r2 prime, and measure the response at r1, r1 prime. Okay. So this is exactly the meaning of density matrix response function. Okay. So that can be compactly written as this expectation where r1, r1 prime times times your response matrix times r2, r2 prime. Okay, so this is a compact way of writing this. Now, just like if you remember the relation between density and density matrix, right? So rho of r is p r r prime, where r and r prime are equal. In a similar fashion, you can get the density response function by taking the diagonal of the density matrix response function. Okay, so chi r1 r2 omega is going to be pi r1 r1 r2 r2. So when r1 is equal to r1 prime and r2 is equal to r2 prime, you're going to get your density response function. Okay, so if you were to compute the density matrix response function, you're going to get the density response function for free. So that is, all the information is already there in this particular case. Okay. All right. Yeah.
How are you seeing these x, y? Physically, what are the xy vectors?
Yeah.
What is your way of seeing? Any picture that you have about them? Like, for example, as we just started, if I wanted to create a spatial response,
Right.
then I would do this kind of projection in order to understand. Any picture you have?
I don't have any pictures, unfortunately, but so the some form of square of this is what you compute, like the transition density that you get in TDDFT codes, for example. Okay, so you are going to be taking a square of this, for example. I think so. You can, right? So if I were to completely neglect the y vector, for example, right? So that would be like a CI coefficient, right? So you can think of it like that. So normally we call this the transition vector, right? Or you could, if you were to take the square of this, you're going to get the transition density, right? Okay. So I think that is the only relationship that I can think about. Yeah, maybe it's a good suggestion to have pictures. Then you can see what I'm talking about. Okay. Yeah. It should be -1. Thanks. Yeah. So delta should be -1. Okay. So thanks for pointing it out. Yeah. So any other questions? Yeah. Right. So now that you see what is the relationship between pi and chi, chi is your density response function. I just call it density response function, right? And corresponding to chi, you can write a chi naught. Okay. So chi naught is just a bare Kohn-Sham zeroth order density response function. So if I neglect all the 2 electron part of it, that is going to give me the chi naught, which in literature we call it the non-interacting response function, right? So what is non-interacting response function? Instead of lambda here, I'll have a lambda naught, where lambda naught is simply diagonal. It just contains the Kohn-Sham matrix elements. Okay, so if you had a truly non-interacting system, you would have a diagonal lambda naught. Okay, so that would be your chi naught. Okay, yeah, and now you can think of a Dyson equation to relate chi naught and chi, right? So you can take the chi inverse and you can relate it to chi naught inverse minus the Hartree kernel and minus the exchange correlation kernel. Okay, so this is the relationship. This is a Dyson type equation which you have here between the interacting response function chi and the non-interacting response function chi naught. Okay, and with random phase approximation, what you do is you completely neglect fxc again, just as before. Okay, I'm going to introduce one more term which is called alpha dependent random phase approximation, where yeah, it's a second order derivative with respect to it is a density functional. Yes. Only for Hartree. Only for Hartree it will vanish. So it is a function of R1 and R2, but no, there is an implicit dependence on the density, right? Yeah. It is initial state dependence. So so right now there is. So see the fx, right? See the fxc is being evaluated at the ground state density matrix, right, or density in this particular. Okay, maybe I will just understand what you're trying to say, but yeah, fine. Okay, so with chi RPA, right, I'm going to introduce one more term which is which is used in so-called adiabatic connection, right? So this is the definition of chi RPA, that we have the non-interacting response function and just the Hartree kernel, right? Now there is something else that I have introduced here, which is chi alpha random phase approximation. Okay, what is chi alpha? I'm going to simply scale the Hartree kernel with an alpha factor. Okay, and I'm going to use it to connect, say, when alpha is 0, I'm going to get a non-interacting response function, and alpha is 1, I'm going to get a completely interacting response function at RPA level. Okay, so this is chi RPA and chi alpha RPA. Just keep that in mind, right? So this pretty much completes our connection to spatial response function, right? Now I would like to, any questions at this point? So I guess I just wanted to introduce how you start from the fundamental linear response TDDFT equations, then you can all the way go to your symplectic eigenvalue problem, and from there going to dynamic polarizabilities followed by the connection to spatial response functions. I hope that connection is clear. Yeah. Okay. Okay. Yes, something I have to learn. Yeah. Yes. So this is just a fictitious system that we have created, and what it will be used for is to connect a non-interacting and an interacting response function. Okay. So you can imagine alpha equal to 1 is a true interacting system. Alpha equal to 0 is Kohn-Sham system. So Kohn-Sham is one fictitious system. But imagine I construct fictitious systems for different alphas, ranging from 0 all the way up to 1. Okay, 1 we reach the real system. So that is the significance of this chi alpha. Okay, right. Now, so far so good, right? It turns out, so chi of course has the information about excitation energies. So if I figure out the poles of chi, I can figure out where the excitation energies are. Okay, but it also turns out that you can connect your chi to ground state correlation energy, which is not very apparent. Okay, so you have constructed this, quantity which is for excitations, but it also gives you ground state correlation energy. Okay, so how do we connect that? So for that, what I have done here is first to write the exact energy for a ground state wave function in terms of reduced quantities. You all understand reduced quantities? What are the reduced quantities compared to a wave function? You have density, you have density matrix, right? And similarly, you can have something called pair density, right? So for density, for example, you take the wave function, multiply it by itself, and integrate all coordinates except one, right? Pair density, you do the same thing, you integrate all coordinates except two coordinates, two R1 and R2. That will give you the pair density, right? So if I were to write the exact energy function, I can write it in terms of the density matrix, trace of that with the kinetic energy operator, and then the pair density, okay? Tracing that with the R1, R2 operator, that is your Coulomb operator. And then I have this other term which is just density times the external potential, okay? So this is quite fascinating actually, right? So if I want to write the exact energy function, I don't need the wave function, right? I only need the pair density. In fact, from pair density, I can get one particle density. And then I just need the density matrix, P1. Okay, so this is actually a very nice research problem in itself. Okay, now it turns out if I were to just integrate my response function, right, say over imaginary frequency, for example, there is an integral over d omega here. Okay, that was missing. If I were to integrate chi over d omega, it has the information of the pair density. Okay, so to do that, you have to do a little bit more expansion of this chi in terms of transition densities and so on. What you would notice is that this expansion has the information of pair density minus the uncorrelated part of the pair density. Okay, so this is the information that you have and more terms over there. Which one? Density. I'm sorry, yes. So he's catching all the mistakes. Yes. Yeah, so I missed that. So this should be rho of R. Yes, yes. But I hope in the conference we have used both terms, right? Not in the same talk. Yes. Okay. Huh? Not in the same slide. Yes. Yeah. Yes. Not in the same paper, I guess. Yeah. Okay. So now it turns out your chi has information about pair density. Okay. So which is quite interesting. This is also called zero temperature fluctuation dissipation theorem. So I don't want to use that, but essentially if you were to do a simple contour integral, okay. So if you do a contour integral over chi, actually you're going to get the pair density. So this is quite fascinating actually, going from TDDFT response functions to ground state properties like pair density. Okay, yeah. Yes. Right. This is the correlated portion of the pair density. Yes, yes. So you don't get these individual pieces. You have everything clubbed together. I just wrote it like this. You will get. Yes. So you will get that correlated portion of the pair density. Okay. Zero temperature. Yeah.
So this actually first time was derived by Wright and Turnbull, and where the exact correlation interaction energy human as an integral.
So okay, okay.
So it's basically taken over. That was a many body technique.
I see.
It has been taken over to the
I see. But okay, I know some other paper, some other reference which I used for zero temperature fluctuation dissipation, but so I am not aware of
So
this.
that was divided in the 60s.
60s, I see. I think I think
So that's the most famous paper for the art. So then they show that if you do the regular product function, so
I see. Okay. Yeah. So that I'm not aware of. Of course,
one derives these correlation energies, RP correlation energies derived through the response function, which is known as the
Linhart function. Yes. Yes.
How can it be possible?
Yes, I'm not aware of that. Of course, Ball and McLachlan's paper.
Also, you as well as the students have much of those.
Yes. So the Ball and McLachlan paper definitely has some part of this, some discussion on TDHF to ground state correlation, right? So, and then the zero temperature fluctuation dissipation, the terminology was used somewhere else that I'm aware of. Okay. Yeah. So,
CFD people started using that fluctuation.
right.
Why was known as applied.
Yeah. So for me, it is just simply a contour integration. Okay. So no need of those fancy terms. It's simply a contour integration. And what I would right now show you is that the ground state correlation energy, right? You can get it by this somewhat complicated looking integral. So what you have to do is you have to get a line integral where I'm cranking up the interaction all the way from 0, the non-interacting state, to the interacting state, and I'm computing the pair densities over all the interaction strengths. Okay. So by doing that, I get ground state correlation energy, the RPA correlation energy. Okay. So this is a little bit hard to digest, and there is no way I can discuss this in this short time period. But essentially, the RPA correlation energy is a functional of the response function. Okay. So we have studied so far functionals like GGAs, LDAs, and hybrid functionals. There you could see the functionals being dependent on density, gradient of density, or say the density matrix. Okay. But now we have gone one step further where it is a function of the response function. Okay. Now can you tell me? Yeah. No, you have to integrate over all alpha. You have to integrate over all alpha. Yes, yes. So you can analytically integrate because there's a very simple form for this, right? So yeah, couple of points here, right? Okay, let me just ask this. So you have ECRP, you see this particular form for correlation energy, right? And the total energy is given by this expectation value. So this is like the exact Hamiltonian evaluated over the Kohn-Sham determinant, and then you have the correlation piece. Okay. So from here, can you tell whether correlation energy is local or non-local? It's non-local. So this is a pure non-local type of functional, right? So that is one thing. But this should be I omega, right? Yeah, you're right. Yeah. Yes. So there's so many typos. Apologies. So it should be I omega. No, this was this was okay. Yeah, and there should be a modulus here. Yes, there are a couple of things missing. Yes. Right. The other part I want to point out is this ECRPA, because of this line integral, actually includes both the kinetic correlation as well as the potential correlation. Okay. If I only take the two ends of this integral, it will only include the potential correlation. But because I do this line integral, it actually includes the kinetic correlation as well. Okay. Purely evaluated in terms of response function. So ECRPA has both terms over there, right? Yes, we can get it. You can actually estimate the potential easily. There is no analytical form for the kinetic, so you can just subtract. You can subtract and get the kinetic correlation. So you can get both parts from here. Okay. So fine. Okay. Right. Yes. So you can evaluate the alpha 0 analytically. You can evaluate the alpha 1 analytically. The difference will give me the potential correlation energy. and then I can subtract out and get the kinetic correlation. Okay. There is no double count. There is nowhere any double counting. Okay. So any.
Trying to ask like whether it can be used because it's more like the mini body method. You will be seeing how much the method is able to retrieve the correlation is like that method minus active form.
Yes.
So you are showing that phase density minus that one looking very similar like that, right? You are able to get how much amount of correlation is there in the system.
Yeah, yeah. I mean,
Equation from the top part.
right.
Can we use it to improve the correlation of a method or
So use this as an addition for something else.
as an estimation of how much amount of correlation or
You write it as a line equation and then reiterate with that.
Yeah, I'm not.
Simply way to put it is, for example, how much amount of how strongly correlated my system is if I want to. It's like a molecule. Generally, what I would like increase MD2, then CCSD, etc. The methods.
But these are the only that hard to capture.
Yeah. Okay. Yes. So firstly, that part is. So I think one thing I want to mention is if you were to expand chi, right? So based on the Dyson equation that I was showing. So if you were to expand chi, you will get the series expanded in chi naught v chi naught. I think that's what you're trying to say. So you can actually do that expansion and then say evaluate the second order, third order, and so on. That can be done by order expansion. Okay. Right. Right. That's a very good question. Okay. So I think what Arun had pointed out, there is no exchange and exchange correlation kernel is missing. So now people have done additions to that, right? So this is where you hear about methods like AXK and SOSEX. So these are a couple of methods which are present to add that extra correlation. Right. So there is a system. Yeah. So there is a way to improve it, but the return on these improvements is not that high for across the spectrum of problems. But right, there are double hybrid functionals based on RPA. So I think so, right? Yeah. So okay, so we'll come back to the rung of functionals, which has to be there, right? So what we have discussed right now is the random phase approximation here, and as you can see here, this sits right at the top, the fifth rung of functionals, where you actually have non-local correlation there, right? And I'm just going to show a few applications of this, and then we can disperse. So the RPA approach has two advantages because, as you can see, the energy functional, it has exact exchange. So it is free from one electron self interaction. So there is no issue there. And it also has the correct long range correlation potential. Okay, that has not been discussed so far. So far we were discussing about correct long range exchange potential. But RPA method also has the correct long range correlation potential. And the main selling point of RPA methods is that it includes dispersion interactions. Okay, so if I want to understand the binding of benzene molecules, right, or binding of a crystal, molecular crystal, you can do RPA calculation. It is quite expensive, but you can do this, and you can, without fitting any parameters, you can get the dispersion interactions right. Okay, so that is those are the two main selling points here. So I'm going to just show a few applications. So over here, these are again G21 data set where we are testing the Kohn-Sham functionals like PBE, the generalized Kohn-Sham functionals. I don't know if I can see it right. PB0, right? Then I have MP2 and RPA here. And you can see here for in terms of atomization energies, the RPA errors are quite similar to what you get from PBE or other functions. So some other functions are actually better. So the return is not much here.
Small question. But where we think that this RPA is able to incorporate dispersion because of the non-locality?
It's because of the non-locality. That's correct. Very nice. Yeah. So that is a connection. The non-locality includes the dispersion effects. So dispersion by yes.
Maybe very next question. Why are we calling it as random phase approximation?
Yes. So that is the physics nomenclature, and I wish Manoj was here. So essentially, so this was in the condensed. Call him back, okay? Yeah, so I think so. So this terminology was by Bohm and Pines, who are very famous condensed matter physicists. So what they were studying was the response in electron gas, okay, and they were on in the Jellier model or something like that, right? And what they found was that when you perturb a system with a particular wave having a frequency omega, and then measure the response. There are two types of responses, one which is collective in nature, that is responses which are having the same frequency and they're all coherently adding up, and then some which were local and incoherent. So those incoherent excitations or oscillations, those were cancelling out, okay. So that was called as random phase approximation, or they were assumed to be small and they would cancel out. That was assumption. So that is why it is called random phase approximation, okay. And the collective modes which are oscillating in phase, that is a most important response. So that's how this terminology came up about random phase approximation, okay. And in chemistry, random phase approximation is same as time dependent Hartree, okay. So these are equivalent. So that is much simpler for us to understand, right. So now the selling point here is the interaction energies for the S22 data set. And what you would notice here is a dramatic improvement with RPA methods. You see that the interaction energies are, the errors are reduced by a large amount for this S22 data set, which is made up of molecular dimers interacting with weak interactions. So this is one main advantage. Now the binding of two graphene layers, we all know graphene binds by dispersion interactions, right? So if I take two graphene layers and actually compute the interaction with say some pure Kohn-Sham functional without dispersion corrections, it may not bind, right? So over here, what I'm showing you are couple of methods, and what you see here is the random phase approximation gives you binding energies which are very close to experiment. So this 48 MeV, I think, and this is very close to the experimental value, okay. So this was one of the successes in condensed matter for random phase approximation, that was showing this binding energy to be correct. Okay. Yeah, so there are a couple of other successes. I think I will just discuss one, right? So one of the main successes that I'm going to show is about anions. If you were to ever study anions using density functional theory, suppose you're studying H minus or F minus, and if you were to use sufficiently large basis set, what you would notice with DFT, here it's a B-ellipse functional. If I keep adding the functions, number of diffuse functions to F minus, and I keep measuring R square, that is the spatial extent of the electron that has been added here, what you would notice is that as I keep adding diffuse functions, at some point the wave function keeps expanding. Okay, it really goes to infinity. So basically, DFT doesn't want, or not, I mean pure DFT, I mean exact DFT, something like a B-ellipse functional doesn't want to bind an extra electron. It would rather ionize it. Okay, this is a major problem in density functional theory. Now it turns out this is happening because you have the wrong asymptotic potential. So asymptotic potential, because of self-interaction error, is not attractive enough. Okay. So here I just want to show you some numbers. So if I were to do PBE and compute the HOMO orbital energy, and I think you just had some exercise where computing orbital energies. If I do it for anions, you would see that these numbers are all positive, indicating that if you have a positive HOMO orbital, it means it is unstable, okay, in the Kohn-Sham language. And the reference values, these are the reference ionization potentials, these are all negative. Okay. So if you do Hartree-Fock, actually you get the right sign. Okay, you get the signs right, but these are bound too strongly. Okay. If you do GW, Even GW has some issues. I think Arun was saying if you have a wrong starting point, you will have wrong answers. This GW was based on PBE and you're getting the wrong answers over there, right? And here this is a method that I had worked on. So if you use random phase approximation, you start getting these binding energies much more accurately, okay? So this is a way to do this. I'll just skip this and then I'll just discuss one more success of random phase approximation. So in materials chemistry, there is this famous problem of adsorption of CO molecule, carbon monoxide. Do you guys remember for carbon monoxide, which has a small dipole, where is the negative end of the dipole? Carbon or oxygen, based on your chemistry knowledge? It's on carbon, right? I think if I were to use Hartree-Fock, actually it gives me the wrong dipole sign, okay? And so if you want to absorb CO on this say on metal surfaces like copper surface, right? You need to get the right electrostatics and the right interaction between dispersion interaction between CO and the metal surface. And if I use commonly used functionals, they will all say that on copper surface, carbon monoxide molecule would adsorb on the hollow sides. So you have a copper lattice, copper atom sitting in a lattice, you have hollow spaces and then on top, that is on top of the copper atom. What you would notice is that all these functionals say that the carbon monoxide should adsorb on the hollow side, okay? Experimentally it is proved that the carbon monoxide actually adsorbs on the on top side, okay? So you see all these functionals are getting that part wrong, right? That only when you start using random phase approximation, right, say based on PV density matrix or PV0 density matrix, right, you get the right ordering of this. So this was one of the major successes of RPA method or non-local functionals to get this right. I think to this date, I'm not sure if any of the hybrid functionals get this right, okay? So this is one of the outstanding challenges that you have. Okay, so I think with that I will end here, right? So we have discussed I think a lot of functionals throughout the conference, and we'll end on this pretty much higher rung functional. And I think you hope that you can see the advantages of systematically developing functionals. Okay, with RPA there is much more systematicity because you have very simple many body picture that you can use, and you can get the form of the functionals. Okay, so I think on a surface periodic calculation, these are not clusters because you'll have other issues, right? No, because metals have this issue because they have the zero band gap. So doing any wave function method becomes much harder. So if I can't do MP2, for example. But even if it is a small cluster, no, Arun, I think the other challenge is because even if it is a metal cluster, you still have a small gap, and MP2 will not be sufficiently capturing all the interactions, for example, right? So MP2 computationally is similar to RPA. RPA is slightly lower. You can do that, but you will not capture all the necessary physics. It's N4, and in periodic systems it's N4K square, I think. MP2 is N5, it's much more expensive, but I think the physics is also not there. It only includes second order dispersion interactions. So there are both issues. So the many body dispersion is also based on the random phase approximation, but for some sort of a Drude oscillators or something like that. Yeah. These are what? So you're asking if they have deep. I'm not sure, but I don't think that matters. No, for the ordering, that ordering doesn't matter. Huh. I am with this between the hollow and the on top side. Yeah, I will be suspicious because the dispersion will not change much, right? Between right, right. I'm saying, will it really change so much between in based on D corrections, right? No. I'm talking about the difference between the on top and the hollow sides. Will the D correction really change, right?
Maybe
So I will check it out. I will check it out.
if you want to see, you have to calculate, I guess.
So yeah, he doesn't want me to. Yeah. Yes, that is rest of the talk. Yeah, so it is sensitive. So there are issues there, the density corrections. So I wanted to talk about the density correction some other time,
Keep
perhaps.
it after after
Yes.
dinner.
After dinner, yes. They're not much different. But I'll show you some things later. So
Any
density correction is
questions
important.
from the students? From students' side? Okay, you guys know the terrace hall? By the
Yes,
way?
something.
Yeah. Okay. Yeah.
Is the same as the one which we get when we compute like GCMC simulations, like for this porous materials?
What is GCMC?
Grand Canonical Monte Carlo?
Okay.
I mean,
yes.
actually, I'm new to DFT. I'm good. I'm familiar with this classical simulations thing, and like for porous materials, like in like we generally compute these isotherms.
Right.
And we are more interested in isotherm data, and I never looked into this adsorption energy specifically, but the output has adsorption energy term.
Yeah, so what we are doing is without any enthalpic corrections here,
Okay.
right? So, but what you would be doing in GCMC would be you'll be sampling many configurations as well as including temperature effects, right? So over here, this is just simply the without temperature energy difference,
Okay.
right?
I wanted to know like how both these adsorption energies are different, like to get an idea on what it is actually.
Both means
I mean, the one which we get via GCMC simulations and probably the one via DFT calculations. Yes.
yeah.
Oh. Okay. Oh, it's a different energy terms which were used, like free energy terms.
Okay. Okay. We talk while walking to the terrace hall. That's better, right? Yeah. Okay. Fine.